Okay, welcome to the deep dive. You have sent us a truly fascinating stack of sources here. It's like well, a treasure trove covering everything from the intricate rules of financial markets to the cutting edge of artificial intelligence.
It really is. Two complex, seemingly quite different fields, but your material gives us this unique lens into both.
Exactly.
Yeah.
So our mission today is pretty clear. We're here to take your material, dive deep into it, and really extract the absolute best nuggets of knowledge.
Yeah, help you cut through all that complexity.
Right, and get straight to the good stuff, those sort of aha moments. Think of this as your custom guide to becoming instantly better informed on what really matters in the sources you shared.
So based on what you provided, we'll be exploring two main areas. First, we'll unpack the intricate world of financial options and some key strategies for using them.
And then we'll jump into the equally fascinating landscape of deep learning, looking at how those, powerful models work and what they're actually used for.
Ready to dive in?
Let's do it. Let's unpack this, starting with financial options. You gave us some great material here explaining the fundamentals. Um, at its core, what is an option contract? How does it differ from, say, just buying a stock?
Well, simply put, an option contract gives the holder the right, but crucially not the obligation, to either buy or sell an underlying security
Okay.
at a specific price before a certain date. And that not the obligation part is really key. It gives you flexibility you just don't have with owning the security outright or a futures contract.
Okay, so there are two main flavors then. Calls and puts. How should we think about those?
A call option gives you the right to buy the underlying asset at a fixed price.
Right, to buy.
And a put option gives you the right to sell it at a fixed price.
And that fixed price is what the sources call the strike price, yeah?
Yeah.
How does that relate to the actual market price of the underlying security?
Correct. The strike price or exercise price. It's fixed when you enter the contract.
Yeah.
But the market price of the underlying security, like a stock, well, that's fluctuating constantly. So the value of the option is fundamentally tied to the relationship between that fixed strike price and the moving market price.
I see. So the price you pay for an option isn't just arbitrary. The sources break it down into two core components, intrinsic value and time value. Can you maybe explain what those represent?
Yeah, think of the option's price as basically the sum of two parts. Intrinsic value is the immediate value the option has if you were to exercise it right now.
And how do you calculate that?
So for a call option, it's the maximum of zero, or the current security price minus the strike price. We can maybe call it max zero as 0x.
Okay.
If the market price as zero is above the strike, X, you have positive intrinsic value. You could, buy at X using the option and immediately sell it as zero for a profit, theoretically.
Makes sense.
If as zero is at or below X, the intrinsic value is just zero because, well, you wouldn't exercise it.
Right. No point. And for a put option?
It's basically the opposite logic, the maximum of zero or the strike price minus the current security price,
Right.
max zero, X as zero. So if the market price is below the strike, it has intrinsic value. You could buy low on the market and sell higher at the strike price using your put. If I0 is at or above X, intrinsic value is zero again.
Okay. So intrinsic value is essentially how in the money the option is right this second. What about time value then? The sources say that's the more complex part.
Time value is, well, it's everything else. It's the difference between the option's total market price and its intrinsic value. This value exists because there's still time left before expiration.
Ah, time for things to change.
Exactly. Time for the option to potentially gain more intrinsic value because of future price movements.
Ah, the potential. And the sources list factors like expected volatility sigma, interest rates, and time to expiration t as influencing this time value. Which of those typically has the biggest impact? Why is volatility so important here?
Volatility is usually a huge driver. Higher expected swings in the underlying price mean a greater chance of a big favorable move happening before expiration, which naturally increases the option's potential value, its time value. And more time until expiration also means more opportunity for that big move to happen. So time value is higher for longer dated options too. Interest rates play a smaller, more technical role related to the cost of carry.
And that time value doesn't last forever, does it? It like decays over time.
That's a critical point, absolutely.
Right.
Time value erodes away. As an option gets closer and closer to its expiration date, its time value approaches zero. By the time you hit expiration, an option's value is only its intrinsic value, if it has any.
The source material shows us that example with AAPL stock option prices, table 4.1. What does that table specifically illustrate about these concepts we've been discussing?
Yeah, looking at that table, you can see pretty clearly how the option prices systematically change. For call options with the same expiration date, the ones with higher strike prices are cheaper
Right.
because they have less or maybe zero intrinsic value and, frankly, less chance of getting deep in the money. For puts, it's the opposite. Higher strikes mean higher prices.
And you also see that options with longer time to expiration, like the August options compared to the April ones in the table, are more expensive across the board for similar strikes. That difference is primarily the time value at work.
And the sources point out that in that specific table, all the listed option prices were actually higher than their intrinsic value at that moment.
Yes, exactly. Meaning they all still had some time value on that particular date, which was March 22, 2012.
Okay, now here's where it gets really interesting for me. How these things actually pay off at expiration. The sources talk about a kinked or asymmetrical payoff pattern. What does that mean? How is it different from something, I don't know, linear like a futures contract?
Yeah, unlike a futures contract where your profit or loss is basically a straight line, directly proportional to the price change of the underlying.
Right.
Options have these, well, sharp angles or kinks in their payoff diagrams. The most important asymmetry, probably, is that the potential loss for buying an option is limited just to the price you paid for it.
Okay, cap downside. Exactly. While the potential profit can be much larger or even, theoretically unlimited for something like a long call.
Right. Limited downside, potentially much larger upside. So for a simple option position, like just buying a call, what's the break-even point? Where do you neither profit nor lose money at expiration?
Okay, for a simple call option that you bought, you break even when the security price at expiration reaches the strike price, plus the initial price you paid for the option.
Got it.
You need the price to go above the strike by at least what you paid just to get your money back.
And for simple put you bought?
For a put you bought, you break even when the security price at expiration falls to the strike price minus the initial price you paid for the put.
Okay.
You need the price to fall below the strike by at least what you paid for it.
Okay, that gives us the basic building blocks then. The sources then introduce the idea that you can actually combine these basic call and put positions to create more complex strategies with very specific risk and return patterns.
Exactly. And this is where you start tailoring those asymmetric payoffs to match different investment goals or different market outlooks.
The first strategy mentioned is the protective put, sometimes called portfolio insurance.
Mm-hmm.
What problem is that designed to solve?
It's really a classic defensive strategy. It's for someone who owns an underlying security, like a stock, but wants to protect themselves against a large drop in its price.
Okay.
And you achieve this by buying a put option on the stock you already own.
So the stock gives you the upside if the price goes up,
Right.
and the put option acts as a sort of parachute if the price falls.
Exactly. Like figure 4.8 in the source illustrates conceptually, it provides a floor for your total payoff, typically right at the strike price of the put. If the stock price rises above the strike, you still participate in those gains, although your net return will be slightly less than just holding the stock because, well, you paid for the put.
So that downside protection isn't free, which, yeah, makes total sense. It's like buying insurance, just like the name suggests.
Right.
What about a totally different approach? The straddle strategy really caught my eye. It feels like a very different kind of bet.
It is, yeah. With a straddle, you buy both a call and a put option on the same underlying security.
Both, okay?
Both. Same strike price, same expiration date, and crucially, you don't hold the underlying security itself.
So you're not really betting on whether the price will go up or down then?
No, exactly. You're betting on volatility.
Yeah.
This strategy profits if the security price makes a large move in either direction, up or down.
Okay.
Enough of a move to cover the combined cost of buying both the call and the put. Figure 4.9 in the source shows that distinctive sort of V-shaped net payoff structure.
Okay, so you need a significant swing, one way or the other. And your break-in points are now on either side of the strike price, right? Accounting for the cost of both options you bought.
That's the key. You have two break-even points. And the sources really emphasize that when investors choose option strategies, the most important considerations are their view on the expected direction of the underlying security price change and their view on future volatility.
Direction and volatility, that framework makes a lot of sense for, navigating the potentially infinite ways you could combine these options.
Right. Now, taking a pretty significant step back, Your sources also give us a deep dive into a completely different but equally complex area, deep learning.
Right, we're shifting gears here, from financial instruments to computational models. But, in a way, both are powerful quantitative tools for analyzing and modeling complex systems, just in very different domains.
That's a great point. Conceptually, what deep learning really tries to do is build incredibly complex nonlinear functions to model data. The deep part comes from the specific layered structure they use.
And that structure is built on what we call neural networks. The source shows us a basic diagram, figure 10.1. How should we understand the layers shown there, like input, hidden, output?
Yes. You've got an input layer where your raw features or data points enter the network. Then you have one or more hidden layers.
This is where the sources say the, quote, magic happens. What actually goes on inside those hidden units?
Well, each unit, or neuron, in a hidden layer takes a linear combination of the inputs from the previous layer, basically just a weighted sum.
Okay.
But then crucially, it applies a nonlinear transformation to that sum. These transformations are critical, and they're what the network actually learns during training.
So it's not just a simple sum. There's this extra nonlinear step. And that's provided by something called an activation function, like the source mentions ReLU. Why is that nonlinearity so essential?
Absolutely essential. If you only had linear transformations in each layer, no matter how many layers you stacked up, the whole thing would mathematically just collapse back down into a single linear model. It wouldn't be any more powerful. The nonlinearity provided by functions like ReLU, which stands for rectified linear unit, it's simply max 0, ZO, allows the network to model complex nonlinear relationships in the data. Figure 10.2 shows the ReLU function. It's flat at 0 for negative values and then just goes up linearly for positive values.
And the bias term in that linear combination essentially just shifts where that ReLU function starts to turn on, right?
Precisely. The sources give a simple example showing how combining even just a couple of these nonlinear units can capture something like an interaction, like x1 times x2, which a simple linear model just couldn't represent directly.
And the deep part of deep learning comes from having multiple hidden layers then.
Exactly. Multi-layer networks allow the model to build up increasingly complex and abstract transformations of the input data, layer by layer. Early layers might detect simple patterns like edges in an image. Later layers combine those to detect shapes, and even later layers might combine shapes to recognize objects. Built hierarchy.
The source uses the classic MNIST handwritten digit dataset as an example. What exactly is that dataset, and how is it set up for a neural network?
Right, the MNIST dataset. It consists of thousands of small 28 by 28 pixel grayscale images of handwritten digits from 0 through 9. The task is simply to classify which digit is in each image.
Okay.
So the input to the network is the raw pixel values. That's 784 numbers, 28 times 28, and the output needs to tell us which of the 10 possible digits it is. This is often represented using what's called one-hot encoding, basically a vector of 10 numbers where one is 1 for the correct digit and all the rest are zeros.
The architecture described in the source for MNIST is relatively simple, right? An input layer, two hidden layers, I think 256 and 128 units, and then an output layer. What does that simple structure imply about the model's complexity, though?
Well, even that seemingly simple network for MNIST has a massive number of parameters to learn. The source notes it's got 235,146 parameters. Yeah, so that gives you a sense of the scale and complexity involved, even in what's considered a pretty basic deep learning example today.
And for classification problems like this, the output layer often uses the softmax function. What does that do?
Softmax is a neat function. It takes the raw outputs of the last layer and converts them into a probability distribution over the possible classes.
Okay.
So for MDIST, it would output 10 numbers that all sum to 1, representing the model's estimated probability that the image is a 0, a 1, a 2, and so on, up to 9. And the source mentions that this type of network achieved a dramatic improvement in test error rate on MNIST compared to simple linear methods, which really highlights the power of that nonlinear layered structure.
So that's the general structure. But the sources also dive into specialized network architectures for different types of data. Are there networks built specifically for images, for instance?
Oh, absolutely. For images, convolutional neural networks, or CNNs, are really the go-to architecture. They're specially designed for spatial data like images and are, well, loosely inspired by the visual cortex in biology. They are incredibly effective for tasks like image classification or object detection.
The key layers here sound complex: convolutional layers and pooling layers. Can you maybe break down what those are doing?
Okay, so convolutional layers use things called filters. These are small, learned patterns or templates. You can think of a filter that looks for horizontal edges, maybe another for vertical edges, another for corners.
Okay.
These filters effectively slide across the entire image. And as figure 10.7 shows conceptually with that tiger image example, areas of the image that strongly match the filter's pattern get a high value, a high activation in the output. Different filters learn to detect different features automatically from the data.
So the network actually learns what features are important to look for in the image itself.
Exactly. Then, following convolution, you often have pooling layers. These layers help to condense the information and make the network a bit more robust to variations. Max pooling, for instance, is common. It just takes the maximum value within small blocks of the feature map coming out of the convolutional layer.
What does that achieve?
It reduces the size of the representation, making it more computationally manageable, and it also adds some invariance to the exact position of a feature. So if an edge is detected slightly shifted in the image, pooling can still capture that the edge feature is present in that general area.
Are there any, clever tricks they use with image data during training? The sources mentioned data augmentation, shown in figure 10.9.
Data augmentation. Yeah, it's a simple but super effective technique, especially for images. You basically randomly apply minor distortions to your training images, things like slight rotations, shifts, zooms, maybe horizontal flips, but you keep the original label. This creates lots of new, slightly different training examples on the fly. It effectively makes your dataset feel much larger to the model and acts as a form of regularization, helping prevent the model from overfitting to specific image orientations or positions it saw in the original training set.
And the source talks about using pre-trained CNNs, like ResNet 50 trained on ImageNet. What's the advantage there? Why would you do that?
This is incredibly powerful, especially if you don't have a massive data set of your own. See, large networks trained on huge benchmark data sets like ImageNet, which has millions of images and thousands of classes, they learn very powerful general-purpose image features in their early and middle layers. Features like edge detectors, texture detectors, shape detectors. So you can then take these already learned layers, maybe freeze their weights so they don't change during your training, and essentially use their output as the input features for your new specific image task, even if your task has much less data. Figure 10.10 shows examples of ResNet 50 classifying images like a flamingo or a cat, using these powerful pre-trained features. It's a huge time saver and often boosts performance.
Okay, so CNNs are specialized for images. What about data where the order of the information really matters, like text or time series?
Right. For sequential data like text documents, audio signals, or financial time series, recurrent neural networks, or RNNs, are designed specifically for this. Figure 10.12 gives a sort of conceptual look at how they process sequence input step by step, kind of unrolled over time.
The core idea seems to be that the network has a kind of memory, or persistence from one step to the next.
Precisely. That's the key difference from feed-forward networks like the basic ones or CNNs. The hidden state of the network at any given time, step 10, depends not only on the current input at step 10, but also on the hidden state from the previous step 10.1.
Feedback loop.
Exactly. This feedback loop allows the network to build context and remember information from earlier parts of the sequence. They also typically share the same set of weights across all time steps, which makes them efficient for sequences of varying lengths.
The sources apply RNNs to document analysis using the IMDb movie review dataset. How do they handle text data? I mean, vocabularies can be huge, right?
Yeah, that's a major challenge. This is where the embedding layer comes in, which is a very common technique for text with deep learning. Instead of representing each word with a massive, mostly zero vector like maybe 10,000 dimensions for the IMDb data, if you have a 10,000 word vocabulary where only one position is on.
Very sparse.
Exactly. Very sparse and inefficient. An embedding layer maps each word to a much lower dimensional dense vector space, say maybe 32 dimensions, as shown conceptually in figure 10.13.
And this lower dimensional representation can actually capture some semantic meaning, like words with similar meanings ending up closer together in this embedding space.
Yes, that's the really powerful part of embeddings. They learn to represent words in a way that captures relationships and meaning just from the context in which words appear. These embeddings can be learned from scratch during the training of your specific task, or you can use pre-computed ones like Word2Vec or GloVe that were trained on massive text corpora.
Interesting.
And the source notes that using a more advanced type of RNN called LSTM, long short-term memory, improved accuracy on the IMDb reviews compared to a simpler RNN. LSTMs have special mechanisms, gates, that help them remember context over very long sequences, which is often needed for understanding something like a full movie review.
Okay, LSTMs for long sequences. They also apply RNNs to time series data using NYSE stock market data. How does an RNN approach a time series prediction problem like that?
Yeah, this shows how RNNs can be applied to sequential, often autocorrelated data where future values are related to past ones. Figures 10.14 and 10.15 illustrate this kind of setup. You essentially set up the problem by feeding the network a sequence of recent past values, like a mini-series or a look-back window as input, to predict the next value in the series. For the NYSE log volume data example in the source, they use lagged values of log volume, maybe returns, and volatility as sequential input to predict the next day's log volume.
And how did the RNN perform compared to, say, traditional methods like a linear autoregression model on that specific data?
Well, the source found that the RNN performs comparably to a traditional linear autoregression, or AR, model on the log volume data. Both achieved R-squared values around 0.41-0.42.
So similar performance.
Yeah, in that case. Including the day of the week as an additional predictor actually improved both models similarly, up to R-squared values around 0.46, major 0.47. Figure 10.16 shows a forecast plot from the RNN that, looks quite reasonable, tracking the observed data fairly well.
So even though the RNN and AR models both use lagged values, the RNN has this sort of sequential processing with shared weights and that internal hidden state plus the nonlinearity,
Right.
while the AR model just uses the lagged values directly in a simple linear equation.
That's the key structural difference, yes. The RNN's architecture, even when applied to a relatively simple time series problem like this one appeared to be, has the potential to capture more complex nonlinear time dependencies than a standard linear AR model, if those dependencies actually exist strongly in the data. Sometimes they don't, or the linear model captures most of it.
Okay, so we know the structure in some specialized types of networks, but how do these things actually learn? How are these incredibly complex models with potentially millions of parameters actually fit to the data? It sounds really hard.
It is. It's a genuinely difficult optimization problem.
Mm-hmm.
The core idea, though, is called gradient descent. You start with some initial guesses for all the model's parameters, the weights and biases,
Right.
and then you iteratively adjust them to minimize some error function, which measures the difference between the network's predictions and the actual target values in your data. You make adjustments by moving the parameters in the direction of the negative gradient, basically, the steepest downhill direction on the error surface, as figure 10.17 tries to illustrate conceptually.
And the specific algorithm that makes calculating those gradients efficiently for these deep layered neural networks possible is called backpropagation.
Exactly. Backpropagation is a really clever application of the chain rule from calculus. It allows you to efficiently compute how much each individual parameter, even those deep inside the network, contributes to the overall error,
Well,
and therefore, how to adjust each parameter during the gradient descent step. It works by effectively propagating the error signal backward through the network's layers from the output back towards the input.
and in practice, especially with these massive data sets, they don't usually use the whole data set for each step of gradient descent, do they? They use something called stochastic gradient descent, or SGD.
Right. SGD is pretty much the standard approach for large-scale deep learning. Instead of calculating the true gradient over the entire training dataset, which would be computationally prohibitive for millions of examples, you use small, randomly selected subsets of the data called mini-batches. You calculate an approximate gradient based on just that mini-batch, update the parameters, then pick another random mini-batch and repeat. It's much, much faster per update. And, as the sources note, the inherent randomness or noise in these mini-batch gradients also provides a kind of natural regularization effect, which can be helpful.
And an epoch is just one complete pass through the entire training data set using these mini batches.
Correct. You typically train for multiple epochs, meaning you cycle through the entire data set many times.
Now, with potentially millions of parameters, managing complexity and preventing overfitting seems absolutely crucial. The sources discuss regularization techniques.
Oh, absolutely essential. Without good regularization, these incredibly powerful models can easily just memorize the training data, noise and all, instead of learning general patterns that will actually apply to new, unseen data.
Makes sense.
Dropout learning is a really popular and effective one. As shown conceptually in figure 10.19, during each training iteration, you randomly drop or temporarily deactivate a fraction of the units or neurons in a given layer.
So units can't rely too heavily on any single connection or specific set of other units working perfectly.
Exactly. It forces the network to be more robust and learn more distributed representations. It prevents units from becoming over-specialized or co-adapting in complex ways that only work for the specific training data samples. It kind of acts like training a large ensemble of many different thin networks simultaneously.
Clever.
What else? Another really key technique is early stopping.
That sounds intuitive. Stopping training before the model has completely memorized the training data, perhaps by using a separate validation set?
Yes, exactly that. Figure 10.18 shows the typical pattern you see during training. The error on the training data itself usually keeps going down and down as you train longer. But the performance metric, like accuracy or error, measured on a separate validation set, which the model doesn't see during the gradient updates, will often start to get worse after a certain point.
Ah, the overfitting point.
Right. Early stopping simply means you monitor that validation performance during training, and you stop the training process when the validation performance starts to degrade, even if the training error itself is still falling. Because at that point, the model is starting to overfit the training data at the expense of generalizing to new data.
So with all this power and complexity, when is deep learning actually the right tool for the job? The sources seem to give some pretty clear guidance on this.
Yeah, their advice seems pretty consistent. Deep learning is particularly attractive, maybe even necessary, when you have extremely large training sets. Think, millions of images, vast amounts of text data, and importantly, when the interpretability of the model itself is not a high priority.
Because understanding exactly why a complex deep network makes a specific prediction can be really difficult, right? It's often treated as a bit of a black box.
Precisely. The internal workings, the interactions between millions of parameters across many layers can be incredibly hard to decipher. They also reinforce the point that simpler models, things like linear regression, logistic regression, maybe lasso for feature selection, often work surprisingly well, are much easier to understand, fit, and troubleshoot,
Yeah.
and might actually be preferred, especially on smaller data sets where deep learning might just not have enough data to learn effectively or might just overfit badly. It's always crucial to consider that performance versus complexity trade-off and probably start simple.
Finally, the sources mention this really strange, almost counterintuitive phenomenon called double descent. What is that all about? It sounds weird.
It is fascinating, and it does challenge some traditional intuition about model complexity. We usually think, based on the classic bias variance trade-off, that test error will decrease as model complexity increases up to a point, but then start to increase again if you make the model too complex and it starts overfitting the training data.
Right, the U-shaped curve.
Exactly. That point where training error hits zero or near zero is often thought of as the point of maximum overfitting. But double descent describes a phenomenon observed in certain settings, particularly with very highly overparameterized models like modern neural networks, trained with specific methods like SGD, where the test error can actually decrease again as you increase model complexity well past that traditional interpolation point where training error is zero. Figure 10.20 shows this concept.
That seems to completely fly in the face of the classic bias variance trade-off we usually learn about. How is that possible?
It does appear that way initially, doesn't it? But the sources suggest it doesn't necessarily invalidate the core trade-off idea entirely. It seemed to highlight some nuances perhaps in how we define model complexity in these ultra-high dimensional spaces and how specific training algorithms, particularly SGD, behave. The idea is that among all the models that perfectly fit the training data, interpolate, SGD might tend to find solutions that are somehow smoother or have other implicit regularization properties that allow them to still generalize well to new data, even though they have zero training error.
So it's like there are good ways and bad ways to perfectly fit the data.
Something like that.
Yeah.
It helps explain why sometimes training these massive networks until they achieve near-perfect training accuracy can, perhaps surprisingly, lead to very good test performance in practice. It's an active area of research, understanding exactly why and when it happens.
Wow. Okay. We've really covered a lot of ground in this deep dive thanks to the material you sent over. We've journeyed from the very specific structured world of financial options,
Yeah.
understanding their basic characteristics, how their price breaks down into intrinsic and time value, and how you can combine them into strategies like protective puts for defense or straddles for betting on volatility.
All the way to the vast, sometimes bewildering landscape of deep learning. We explored the layered architecture of neural networks, the absolutely essential role of nonlinearity and activation functions,
Right.
looked at specialized types like CNNs for images and RNNs for sequences with memory, got a feel for how these massive models are trained using iterative optimization like gradient descent and backpropagation, and touched on crucial practical techniques like dropout and early stopping to manage their enormous complexity.
And by digging into your sources, we've tried to pull out the key concepts, use specific examples from AAPL options to MNIST digits, IMDb reviews to NYSE data, and get some insights into when these powerful tools are most applicable. Hopefully, we've cut through some of the noise to give you a clearer understanding of these distinct but, well, deeply interesting areas.
Definitely. So maybe here's a final provocative thought for you to ponder after all this. Consider how these two areas, financial options and deep learning, while they seem so different in their applications, both fundamentally involve using sophisticated quantitative methods to model complex systems. One trying to model market behavior and manage financial risk, the other trying to model intricate patterns in data for prediction or classification. What might the similarities or perhaps the differences in their fundamental assumptions or maybe their inherent limitations tell us about the universal challenges of trying to understand and work with complexity in the world around us?
Or maybe, how might the lessons learned from training these massive, over-parameterized models in deep learning, like that strange double descent phenomenon we just talked about, how might that challenge or maybe reinforce traditional notions of model fitting and complexity, even in seemingly distant areas like quantitative finance? What really stands out to you after this deep dive? Something to think about.